All righty, welcome everybody to the March edition of Westwatch. Today's session is going to be on the El Nino Southern Oscillation. We're calling it a retrospective, and I'll explain a little bit about that title in a second. So what is Westwatch, in case this is your first attendance? It's a monthly webinar series that brings together NOAA staff and our partners from across the region to share information about climate observations and impacts across the West. And we have two formats. One where we have a specific topic, and that's this edition's format. And then every other month, we also have a general climate overview, and we had one of those in February, and we'll do another one in April, and we tend to do this on the third Tuesday of each month. I do also want to let folks know that we're recording this, and we've been posting the videos. We're getting a little faster at posting, and they are up here at noaa.gov/westwatch, and please give those a check if you're interested, or spread the word that those are available. So today's topic, the El Nino Southern Oscillation. And the reason we're calling this a retrospective is that this entire webinar series, the Westwatch, was started in August 2015. And one of its stated goals was to improve external communication of changing climate conditions, including, but not limited to, El Nino. So I think we're going to be sticking very much with that theme today. And on this slide, I'm just showing the sea surface temperatures from the year 2015, the annual anomaly, and you can see that telltale kind of El Nino anomaly stretching across the Central Pacific. And at the right was an infographic from from NOAA Fisheries, showing kind of the roller coaster of ocean condition ecological change over a number of years. But 2015 was a very, very large event, and I think it drew a lot of attention, both the interannual variability we can experience in the North Pacific, as well as kind of ENSO more specifically. So on this webinar, we're going to get a chance to revisit some of our knowledge around ENSO and its connection to that climate variability that we experience. We'll hear a bit about what we've learned since this 2015 event, and we'll also hear about things that perhaps we've known for a while, but that have been illustrated in some of the conditions of the last couple of years. So a bit of housekeeping first. I want to ask one quick poll question about the audience's interaction with Westwatch before. So here you go. If you wouldn't mind filling that out, if you've attended Westwatch before, or you've been an infrequent attendee, or an all the time attendee. Give that a little bit of time to let it run. Great, I'm going to close the poll now. Hopefully you're seeing the share, but of the almost 60 attendees on, it looks like almost half are first-time attendees, which is great, so welcome. And these housekeeping messages will be brand new to you. Each of our speakers will talk for about 12 to 15 minutes. We'll do some questions, and if you could enter those in the question box to the right, we'd appreciate it. We'll do a little Q&A after each speaker, and then again at the end. And this session is going to be recorded, as I mentioned earlier, and you'll also receive a post-webinar survey that should pop up right when this concludes. Today's speaker, we really have an all-star cast, and I'm very appreciative for these folks' time for joining us. Michelle Leroux is from the Climate Prediction Center in College Park, Maryland. Nick Bond from the University of Washington, and also serves as the Washington State Climatologist up in Seattle. And then Nate Mantua, who is at the Southwest Fisheries Science Center in Santa Cruz. And Nate informs us there's some pretty severe weather there. So if he blinks out, that there are some power disruptions happening there. So we'll hope for the best, at least for the next 45 minutes or so. And the way we'll go through this is I'm going to pass things over to Michelle, and I will give her a brief presentation a brief intro. Michelle is a physical scientist at the Climate Prediction Center, where she is lead of the ENSO team. In addition to her research work in subseasonal to seasonal climate prediction, Michelle is a skilled communicator and has been a key contributor to the ENSO blog on climate.gov. So if you're interested in ENSO topics, please do not pass go. Go check out the ENSO blog, some really excellent content there. And Michelle, I'll turn things over to you.
All right, great. Thanks so much for having me here today. I think it's really exciting to look back and see what we've learned since the 2015-16 El Nino. And, you know, personally, I think we learned a lot since the 2015-16 El Nino. I think climate scientists for a while, you know, knew about these concepts of probability and uncertainty and how different ENSO flavors, you know, kind of tie into all of this. But I think 2015-16 El Nino was special because a lot of people assumed that the impacts would be very similar to the 97-98 El Nino, and they definitely weren't. And I think on some level that was a good thing, because I think my impression is that the users and the people who communicate these forecasts have gotten a lot more sophisticated about the nuances of ENSO. And so I think, you know, on some level, the folks who are listening in now should congratulate themselves on this, because I really do see a lot of evidence out there that these concepts are really starting to sink in. And this is a graphic, it's an animation, obviously, of sea surface temperature anomalies in the tropical Pacific right now. And if you've been paying attention over the past month or so, we've transitioned from a La Nina to ENSO neutral. And potentially down the road, come fall and winter, we may have another El Nino on our hands. So this is a good time to go over those concepts that we've learned since the 2015-16 El Nino. So first off, why do we even consider ENSO? Why do we care? Well, as many of the folks on this call know, there are very widespread impacts over the globe, and they're very seasonally dependent. Depends where you are in the hemispheres and different regions. Over the contiguous United States, of course, our maximum impacts tend to be during our winter and early spring. But in other sections of the world, it would be a different timing. And it's clear that in the tropics, the impacts are much more widespread and profound, which reflects the changes in the overturning circulation associated with ENSO. And then as you get farther away, they become a little bit more confined. And so the main advantage here of ENSO is that it often forms before the seasons of maximum impacts. So it's not so important necessarily to get the exact timing of the transition right, as it is that it just forms sometime, you know, some months, 6 months prior to the maximum impacts. That's where we get the gain and the predictability from. And this is I'm going to have a bunch of links at the bottoms of these slides. And if any of these topics are interest of you, I would check this out. These are all sourced from the ENSO blog, and various writers have contributed to this through the years. This particular plot on the bottom right there is showing the average skill score. So we have these measures of how well our seasonal forecasts do over the United States. And what you can see there, and Tom put this together, that El Nino and La Nina tend to have higher accuracy in their forecasts when they occur than if we're neutral. Neutral just simply means there's no El Nino or La Nina signal. So we all know that users really like summary information. Number one question we get is, what is the general impact for La Nina and El Nino over the United States? And so we have these schematics, and of course they're very broad brush, but they give you a general sense of where the jet stream is and where you expect wetter and colder and drier, warmer conditions. And this is nice as a first cut, but as we learned, particularly in the 2015-16 El Nino, is there's a ton of variability here. It's not so much the means that you have focus on. You also have to focus on the spread. And so these are postage stamp plots that we have now introduced and roll out with almost every single winter outlook update the CPC does, it shows the winter precip anomalies and winter temperature anomalies that you expect during La Nina, but it shows it for each winter period. So these are all events in the historical record going back to 1950 and what happened over the United States. So let's just look at the precipitation real quick. And over the West Coast and California in particular, you might notice there's a lot of browns there, which indicate below average rainfall. And in general, that's what does happen on the average. But then there's these big exceptions, right? We have the like 2010-11 event where we have more increased rainfall over Southern and Central California. And while it's not on here because it just happened, we're certainly going to see another one of those exceptional patterns with the 2022-23 La Nina that just left us. So it's important to keep that uncertainty in mind. And so how do climate scientists express uncertainty? Well, we do that in terms of probabilities, and we provide the percent chance of various outcomes. We have three categories that NOAA Climate Prediction Center focuses on. Is near average, below average, and above average. And they issue these probabilities across the entire United States on the third Thursday of each month. And it's important to keep in mind that in the plots themselves, the favored category is shown. So here is an example from 2014-15 where the southern tier of the United States had probabilities favoring a wetter winter. But that at most, that probability is about 43% chance. And so we should always be mindful that there's always this percent chance of below normal and near normal with these. And then of course, the white regions, what we call equal chances, which means that we really don't have any signals to go on. And so it's basically a coin flip if a coin was three sides. So another thing I think we've learned to appreciate a little bit more amongst especially the users, is that there's probabilities given for the chance of El Nino, La Nina neutral. And so there's this plot on the left here showing the bars. And this was issued back in November. And at that time, we were already in a La Nina. We were expecting that third dip La Nina to continue. For DJF, for the December, January, February season, we had a 76% chance of La Nina. And corresponding to that forecast is on the right, the actual winter outlooks that were issued. And this is pretty typical in terms of a La Nina winter. And what's important to notice is that those probabilities there are not super high. Anything above 33% chance in a three category system means you're favoring it. So here in the top right there, those reds are showing that there is a tilt in the odds toward a warmer winter. But those probabilities, particularly over Southern California, were only 33 to 40% chance of above average temperatures. And then if you look at precipitation, we had about 33 to 50% chance of below median precipitation. So that's very common for the impact to have lower probabilities than the chance of ENSO itself. And so a lot of people sometimes get confused over probabilities. They think that, well, that probabilities are a way for you to be right to never be wrong, basically. So we're hiding behind our probabilities, and this really couldn't be farther from the truth. Probabilities actually have meaning, and it's important that we understand that. So just like heads and coin, or heads and tails flip of a coin, which has 50% probability, over a long historical record of coin flips, you should measure out 50% heads and 50% tails. And the same thing can be done with our probability. So if we say there's a 90% chance of above average temperature, then that means that in 100 years, 90 of those years should be above average. That also means that 10 of those years should be below average. And so if we're right, then 10 out of the 100 should be below and 90 of the 100 should be above. If it actually happens 100% of the time, then our probabilities are wrong. So essentially the forecast probability should always equal the historical probability, and that is something you can track. And so we really emphasize here that you have to play the long game. It's not enough to just look at a single forecast. If you treat the probabilistic forecast deterministically, and instead of saying 60% chance of above average temperatures, you say there's gonna be above average temperatures, you're probably gonna be disappointed. So it's really important to keep in mind that it's over a number of different forecasts or a number of different coin flips that you start seeing these probabilities emerge. Okay, so this is a wonderful blog post that was issued very recently by a colleague of mine at GFDL named Nat Johnson. And he put together a really quick little attribution here because, of course, with our La Nina, we had a surprise. And that surprise was the really torrential atmospheric rivers and above average precipitation over the west, which you can see in the left there. And this is a period from December through January. And what he did is that he looked at this in the models, and he asked the question of whether this particular signal was predictable when we made this forecast in November. And he had the advantage of different simulations by the models over history. And so he was able to pluck out the wettest La Ninas and the driest La Ninas. And he asked the question, well, maybe the sea surface temperatures, maybe the flavor of La Nina, that is how it looks on the map, you know, whether it's, you know, more intense in one region, the Pacific, or the other, maybe this could have been helpful for us when we made our forecast. And so he looked at this, and that bottom right panel is the sea surface temperature maps between the wettest La Ninas in his model and the driest La Ninas in his model. And what he found is this map is really like almost very washed out, almost blank here. So yeah, so it did not seem to us, at least in this quick attribution that Nat did, that there was a strong signal here that we could have latched onto. And I think that's important to keep in mind, and ultimately is why we use probabilities, is that sometimes some portion of our seasonal forecasts are fundamentally unpredictable. We can have a tilt toward drier conditions, which you certainly see in the top right there, but every now and then you'll have an unexpected outcome, and that will definitely happen over some part of the country. So one thing I like to remind folks of is that all time scales aren't created equal. A weather forecast is very different from a seasonal outlook. And then there's time scales in between. If you look at, you know, the different drivers of weather and climate, they tend to operate more on certain time scales than others. So for example, ENSO tends to be more of a player in that monthly to seasonal time scale, and the same with trends. But if you're interested in you know, predictability for like week 3, 4, or even week 2, 8 to 14 days in advance, then you get a little bit more information, perhaps from the initial conditions or Madden-Julian oscillation variability. And so those are the timescales that operate for you know, those particular phenomenon. And so I think it's important to keep in mind that it's all probabilities are risk assessments, and it's possible for your particular purpose for you as a user that it is not enough to have 40% probabilities. You might have to make decisions with much higher probabilities, say 90% probabilities, in which case you might want to look at some of these shorter time scales and these other time scales in order to make decisions. So I always say, like what my grandma says at a large buffet, you really should just pick what you can eat. So the last slide I have here is there is a caveat here. You know, while we can look at the historical record and calibrate our models based on that historical record, I think we have to be cogent of the fact that these probabilities may change because of climate change. And here is another image that my colleague Nat Johnson at GFDL with some others put together. And these are departures from average essentially days with an atmospheric river. And so as one might expect, that atmospheric rivers tend to be more common during El Niños and La Niñas. But of course, again, we have that variability. And so it has crossed my mind that if atmospheric rivers are becoming wetter, in fact, I think there's already pretty sound science to establish they are becoming more moisture laden. Perhaps this will start having a stronger imprint on our seasonal average outlook. You know, a La Nina can be dry, but if you get a series of very heavy storms, and that's certainly going to have its mark on seasonal average. So I think we do need to keep that in mind. And so here's some bullets here. I won't belabor this, but I do want to go to this quote that I saw from a Weather Service employee in San Diego, because I thought this really hit the mark, and it really articulates that there is this uncertainty. So in other words, I think we have gotten better over this period at articulating and understanding uncertainty, and realizing that some aspect of seasonal outlooks will be unpredictable. And this particular meteorologist said, La Nina means we're more likely to get warmer and drier air, but it's sort of like rolling a dice. You get more favorable dice rolls for drier, warmer conditions during La Nina, but you can still get that dice roll that we had, which was a colder, wetter winter. And I thought that was just an outstanding example of essentially decision support by this particular Weather Service WFO. So with that, I'll go ahead and wrap up, and we can learn from our other panelists.
Thanks, Michelle. And if folks have questions for Michelle, feel free to put them into the questions box. And while folks are speaking, feel free to do that. We did get one question, and I apologize. I never introduced myself. I'm Joe Casola. I'm the Regional Climate Services Director for the West and playing MC today. All right, so if other questions, oh, here we go. Could the negative IOD plus moderately strong La Nina contribute to a more active MJO pattern? And I think there's a little more commentary. It's interesting to note that a lot of the matching CPC analogs this winter were years from the 50 to the 70s, and potential negative PDO connection. I'll stop there because there's more comments here.
Yeah, I can see that. Yeah, so yeah, I think there are experts out there who would answer this much better than I could, but my understanding is that La Ninas can often, when they're strong enough, tend to damp MJO a little bit. But in, like, for example, this late winter here, we actually had a rapidly weakening La Nina. We were transitioning to neutral. And then we started seeing about the same times MJO variability pick up. So I do think that the decay and the interplay that we saw with the subseasonal may have contributed to a lot of that that precipitation variability we saw. In terms of I think in terms of the PDO, Nate is certainly our expert on this, and he'll articulate and tell you that there is synergy between PDO and ENSO. In fact, often the ENSO will lead the impacts of PDO, but they're different time scales. Again, PDO tends to be more decadal, whereas ENSO has more what we call season to season variability.
Thanks, Michelle. And then one question, what's the average number of ARs for the West Coast? And,
oh, wow, I have no idea.
Yeah, and I actually,
maybe someone else will know that.
Look for maybe Nick or Nate to chime in, but I don't think we actually have a kind of set climatology for atmospheric rivers, because there's different definitions for what you can kind of constitute them, and whether they exist versus kind of, you know, or kind of how strong you want to make the threshold. So I don't think we have a kind of a robust answer for that, but I'll defer to others to pick that up after they do their presentations. Great, well, thank you for the questions, and keep sending those rolling in, keep having those roll in. And let me introduce Nick Bond. Nick serves both in the faculty in the Department of Atmospheric Sciences at the University of Washington, as well as the Washington State Climatologist. His research has advanced our understanding of climate variability and change in the North Pacific with cross-disciplinary attention to both atmospheric and ocean conditions. Nick is credited with naming the blob in 2015. I'm not sure if that's going to be a main feature of his slides now, but you can, when you want to trademark that, you can talk to Nick.
Yeah, that's right. It's going to be my legacy. I dug deep into my vocabulary to come up with that term. And actually, if you could go to the previous slide, just it goes against my religion to start with a title slide. And just for some of you on this call, oh, no, the other direction, if you could. You know, it may seem like quite the whipsaw between, you know, the sort of things that we've been encountering in the Western U.S. in the recent summers and this winter. So anyway, I fulfilled my obligation to start with a cartoon. And what I'm going to talk briefly about here is a follow-up on what Michelle was talking about the what we've learned in the last decade and change about variations in the ENSO. Not all events are alike in the tropical Pacific. And up with is something about the recent preponderance of La Nina events and the kind of interesting aspects associated with that vis-a-vis climate change. And Joe at the very end, assuming we have enough time, will speak a little bit more about that. Okay, next slide. This cartoon is very similar to one of the ones Michelle had. And one of the reasons that I like it is it illustrates a feature of La Nina that along the West Coast we see, and that is that it tends to be a more temporally variable pattern than when we get into El Niños. We'll have the Aleutian low pressure system is definitely suppressed, not as strong as usual, and have more the purple kind of flow with flow out of the Northwest Canada, Western North America, and that's interspersed with periods of a more typical west to east flow across the Pacific. And by comparison, El Niños, it's not like every day is the same, but they tend to be a little bit more kind of consistent during a particular winter. And we've actually seen that this winter, in which the month of February is actually pretty quiet for California. All right, next slide. Patience. As Joe promised, his computer, there's sometimes a delay here. What this is going to show, this cover of the bulletin, the AMS, is about 8 or 9 years ago, a very nice article by Antonietta Capitanvi, kind of illustrating some of the work that had been emerging about the faces or flavors of El Nino, and in particular what this cartoon shows. And Michelle had a kind of similar sort of spin on this, is that not all events are created equal. These colors actually show what the sea surface temperature anomaly distributions are across the tropical Pacific, and there are periods like the winters of 1982-83 and 97-98 in which there is a really warm water in the central and far eastern tropical Pacific, and then other times when the warm water is more confined to the central tropical Pacific near the date line. And if we go to the next slide, there's some work that shows those manifest in the next slide, in different connections or teleconnections to both the atmospheric circulation at higher latitudes, and ultimately the weather. I got ahead of myself. Actually, Nat Johnson's name has come up before. He did some additional work on looking at the patterns of sea surface temperature variability in the tropical Pacific, and used a type of analysis that kind of a cluster type of analysis that showed that the blues where it's colder than normal and how often that occurs, and the reds, those clusters where it's temperature quite a bit above normal. If you look in the lower right corner, that is the classic El Nino pattern, but you can see the really strong ones with a big expression. First, maybe 5% of the time strong near the coast of South America just don't happen that often. And so conceivably, we put a little bit too much emphasis on the kind of weather with those when a lot of other sorts of things happen in the tropical Pacific. Okay, now I promise in the next slide we'll show some of the aspects of these differences in where the sea surface temperature anomalies are in the tropical Pacific and how that plays out in the weather. And quite a while ago here, almost 2 decades ago, Sim Larkin and Ed Harrison at NOAA PMEL did some careful statistical analysis of these so-called conventional El Niños with in the central and eastern tropical Pacific, and how that played out, this in terms of those winters, in terms of precipitation anomalies across the United States versus these dateline Central Pacific El Niños, which are shown on the right. And you can see that there's considerably different patterns, and at that time, perhaps a distressingly low amount of predictability, even if you set the bar at an 80 percentile level, that in terms of just how much you can rely on an El Nino really tilting the odds for either drier or wetter conditions. And of course, just the how it plays out across the United States differs between those conventional ones shown in the middle and the dateline ones shown on the right. All right, next slide. And this will be showing some work by another student of Ed Harrison's, Andy Chiotti, who focused on La Niñas, and it was a similar sort of thing in which not all La Niñas should be considered equal. And what he found in looking at the various events is that what really makes the difference is how often the thunderstorm activity as indexed by the outgoing long wave radiation in the central West Pacific, how many days it was hotter. And rest there because of La Nina conditions, the cold water. So he found that there are 40 days in which there was in this region that there was less of this convection, these clusters of thunderstorms than usual. Then you had, if you look at those top 2 plots there, you had a much more robust impact on the atmospheric circulation over the North Pacific and Western North America, and ultimately a bigger effect on precipitation anomalies across North America. And what's kind of interesting is that suppression of the thunderstorms isn't directly linked to how cold the water is there, but it is in large part related to just the atmosphere doing its own thing, even in the Pacific. it doesn't always get the memo that, oh, the water's cold, there shouldn't be any convection there, and so forth. There's just some inherent variability in the tropics as well as in the middle latitudes. And so what it means is that it's really important to keep track of what's going on in the tropics, in terms of to have a better idea of how it's going to be playing out. All right, next slide. One more little piece of work here that I was involved with, again with Ed Harrison, maybe doesn't get the credit he should, is how the state of the Arctic Oscillation, the AO, a reflection of how symmetric and strong the polar how that plays out in terms of vortex is of regional circulation patterns, and ultimately when the AO is minus, in a minus state, there's tends to be a kind of a wavier jet stream, and there tends to be a higher amplitude to the anomalies that we associate with La Nina and El Nino. And in particular, on this plot here, it shows a composite of the 500 millibar height anomaly patterns for the some La Ninas. This paper is, some time ago, with the AO minus as a whole, and at the bottom with the AO plus, and you can see that there's, especially for the Pacific Northwest, my backyard, with the AO minus La Ninas versus the AO plus La Ninas. This winter as a whole has been AO minus, especially in December, a little bit in January. In February, it went AO plus, and then again in March, the AO went negative. Now, there's very limited predictability in the AO. Some folks are making contentions that are, being vetted. I haven't found them too convincing in terms of our ability to forecast the Arctic oscillation, but perhaps there is some, ultimately there's going to be some predictability there, but we just know that both in La Nina and El Nino, the state of what the Arctic oscillation is doing does seem to matter. Okay, next slide. And here, if memory serves, is going to be what I had talked about at the start here, that I think is a very important point that I'm trusting Joe will be able to cover to an extent right at the end of this webinar, and that is how we've been seeing a lot of La Ninas compared to El Ninos in the last couple of decades. And this is not something we necessarily expected. This is a very busy figure. And what I'd like for you to concentrate on is the difference of the two figures on the right, that basically they show for the last 40 years or so, the differences, the composite difference between the sea surface temperature in the observation versus the climate models that are being used for global climate change projections. And that's at the top, and the sea level pressure pattern. And in the observations over the last 40 years, over a lot of events, we're seeing actually colder water in the tropical Pacific and more of a negative PDO pattern with cold water around the horseshoe shape around Western North America into the far northwestern Pacific, and a weaker Aleutian low, higher pressure than normal. This is something that just the models haven't gotten right. And so the curiosity is why this is. whether it's necessarily just a fluke or going to continue. This is a very active area of research, and I think a very important one, because it really has implications for what the weather's going to be like in much of the globe. From the point of view, if we have a preponderance of El Nino events going forward in future decades versus La Nina events, there'll be consequences. And so with that, I just go with my last slide, having to do just a few words just to sum up. Unlike maybe the feeling among some at least in the climate community, maybe 20, 25 years ago, by no means is ENSO a solved problem. And there's considering, how it's going to play out, maybe some other sources of predictability that modulates their effects. Last 20, 25 years, we learned a lot, but we're still learning. And just to sum up with that last point, that it's, how the ENSO cycle is going to play out in the future is a big deal. And with that, I will close. And thank you.
Thanks, Nick. You got some appreciation for the cartoon, and yeah, I'm sorry I didn't start off with that to hit him right away. We did have one question. Should we be looking at some of the ENSO-related oscillations, like the extratropical northern oscillation index, the NOAA, along with traditional ENSO teleconnections?
Well, sure, and it's not like we don't look at those. The beauty of ENSO, as Michelle mentioned, is that it manifests before its impacts. Many of its impacts are felt, and so it's a source of predictability. And in many of these more higher latitude patterns, like the AL, we only know in retrospect, what has happened. And there, like I said, there may be some sources of predictability that just haven't been exploited yet, but there's not gonna, I doubt if there's gonna be any revolutions there. There's just so much inherent variability in the mid-latitude division that some of those patterns, like the NOAA, the West Pacific pattern and so forth, are just intrinsic, and you can't know until your hand's been dealt. So thanks for the question.
Thanks, Nick. And it's my pleasure to introduce Nate Mantua. Nate's a climate scientist at NOAA's Southwest Fisheries Science Center, where he acts as program lead for landscape and seascape ecology. He's been a leader in examining the impacts of climate change on salmon, and his scholarship identified the Pacific decadal oscillation. And we did get one question that just came in on coastal water levels on the West Coast. So I think we'll hold that until after Nate's slides.
All right. Yeah, and I'll actually maybe address that this topic, ENSO impacts on the West Coast and its marine life and fisheries, one of my lifetime favorite topics. It sort of got me into this business. And the headlines that are in this little inset are pulled from a book that Andy Bakken, a fishery oceanographer, wrote called Patterns in the Ocean, but they're all pulled from 1983, 1984 from the West Coast, in a year or a set of years that experienced major impacts of an unusual ocean, really fierce winter, like the winter that we're living through in California this year. And at that time, it was connected to tropical El Nino. And I was in high school at the time, and this event really caught my attention and got me excited about weather, climate, how it affects fisheries and places where fish go. And yeah, it's something that has had a big impact on my life. So next slide. And it's something that I have spent a lot of time thinking about, working on, and you've seen this slide. And I just wanted to emphasize that one thing that the teleconnections to El Nino and La Nina do is have a major impact on the West Coast ocean when it plays out in the sort of typical way. And in addition to the jet stream and these different temperature patterns, the surface wind field can be very consistently stuck in one configuration. And that kind of black counterclockwise arrow that I've added to the NOAA chart is just to indicate that under some El Nino winters, we can have very persistent, strong counterclockwise winds that involve having strong south-southwest winds along the Pacific coast of the US and sort of southeasterly winds when you get into British Columbia and Alaska. So you get this really strong alongshore poleward wind field, and that tends to favor really strong onshore surface currents in terms of Ekman transports. And that brings offshore water to the coast. It drives the thermocline down, and this happens typically in the wintertime, and it can carry over into the spring. So next slide, please. The other thing that happens with surface winds associated with El Nino and La Nina is big changes in the tropics. So normal year, you have trade winds blowing from the South American side towards the kind of Australia, Indonesia side. And that tends to pile up a warm, thick layer of the upper ocean in the Western tropical Pacific. When those winds relax or even turn around and blow the other way, that releases that atmospheric driving force holding that water in place, and the water surges across the Pacific in a special way in the form of what's called an equatorial Kelvin wave that has its peak amplitude right on the equator. And there's a signature at the surface that you can actually track with a satellite or any kind of surface height measurement, a tide gauge measurement on an island. But the real action is happening on the thermocline, where you can have really large thermocline displacements. And that whole system of coastally or equatorial Kelvin waves surges, and it moves the thermocline down to greater depths, raises the surface all the way to the coast of South America. And as that persists, it can generate coastally trapped Kelvin waves that move away from the equator up the coast of North America, down the coast of South America. And these are concentrated along the shore, and they extend for just a few tens of kilometers offshore. And they raise sea surface heights there and push the thermocline to greater depths. And that can again be by tens of meters on the thermocline depth, but raising sea levels in a sort of a big El Nino winter, maybe as much as a foot above what you'll see in the tide book predictions. And that ends up being a really important impact on storm damage. If you can coincide this elevated sea level with storm surge and a high tide, you know, all those things come together, you get a lot of damage. Next slide. And something that we often see with the big events in the tropics is a substantial warming of the Eastern Pacific with El Nino, and a substantial cooling along the Pacific coast with La Nina. And I just compare consecutive winters where we went from one of the great El Ninos in 1997 through the winter of 98 into the spring of 98, followed by a quick transition to La Nina that summer that persisted for 3 years after the summer of 98. And just take a look at where there's cold water along the Pacific coast. And this is for the month of September, which isn't always the best month to look for El Nino impacts, but it happened to be pretty dramatic in these 2 years. You see a little blue patch off of Cape Mendocino, temperatures there below 60 degrees Fahrenheit. Take a look at the next year, temperatures all along the Pacific coast from British Columbia down to Monterey Bay were below about 56, 58 degrees. And these big changes in surface temperatures aren't just there, but they also extend down to depth. So next slide, please. And here are the cross sections from hydrographic surveys off of Newport, Oregon. Again, this is now in the spring following the big 97, 98 El Nino and then the 98, 99 La Nina. And I've got that red bar in the left panel just to show that when you go from the coast offshore, surface temperatures in April of 98 were about 12 degrees centigrade, so 54 degrees Celsius or so. The 10-degree isotherm was below 100 meters depth. So you have this layer of warmer than 10 degrees from the surface all the way to off the shelf break, and that you can see the coast, the bottom of the sea floor dropping off precipitously as you go offshore. And if you compare that with what happened in the next year, 10-degree water was confined to a very, very thin layer just over the continental shelf. And what is really interesting here is that nutrient-rich waters tend to be coming from depth, and they get upwelled in the spring when the seasonal pattern and the surface winds off the west coast favor north to south consistent winds, and they're pumping up cold nutrient-rich water, and that's fueling a very productive marine food web. In years like 1998, where the surface layer is 100 meters thick and it's warm, you can have upwelling that is simply recirculating this nutrient depleted water mass. And it's really stratified, so it takes a lot of work to penetrate into that nutrient-rich colder water below what is, in that case, a really sharp thermocline. Contrast that with 99. The thermocline is really diffuse. The nutrient supply was much greater that year. Upwelling was much more biologically effective. Next slide. And this has been known for a long time, and again, NOAA has produced some really nice graphics. This is a pretty old one. It might go back to the 90s, I'm thinking, from a publication that was actually focused on the effects of El Nino on marine life off of Peru, but it works about the same for California and Oregon and Washington, that during these warm years with a very stratified upper ocean, it cuts off the nutrient supply, it impacts the marine food web from the base, just reducing the productivity. It changes the whole collection of species to ones that are typically smaller, they're less lipid rich, less nutritious, and lower productivity. And you often see problems for some of the local top predator species that depend on high food supplies, like seabirds. They often have difficulty with their reproductive success. Even marine mammals like California sea lions often have had a lot of pup mortality in their colonies just because they can't get enough nutrition for those nursing juveniles to get big enough to survive. So we see really dramatic effects throughout the entire marine food web, and this has gotten a lot of attention, these kind of bottom-up effects. Next slide, please. And then another thing that is really dramatic in the most extreme years is the impact on some of these big, highly migratory species that are typically found off of Southern California or even Baja California or further offshore, that with that incursion of warm water from the south and from offshore, you'll see things like striped marlin, dorado, bluefin tuna. In 1997, dramatic influx of Humboldt squid came from the south and invaded the Northeast Pacific all the way up to Southeast Alaska. And they stuck around. You know, some of these species really stuck around. And then you have this other thing going on with these sort of more tropical or subtropical blue waters coming in close to shore. It has a major impact on our fisheries because that actually gets a lot of people's attention, get really excited about fishing for things that you might otherwise want to travel to Baja California to fish for. But you also see really hard times for West Coast salmon fisheries under those conditions, that sometimes it can actually impact the survival and growth rates for maturing salmon. It also can put them in places where they're just not easy to access. You know, they go to greater depths and further offshore, just hard to find. Another commercial fishery that typically suffers is the market squid fishery in California, which is one of our biggest fisheries by volume and income, that you typically have a 1 or 2 year major drop in market squid landings during these extreme conditions or in the year following. But they've typically bounced back really fast after those conditions passed. Next slide, please. And again, Pacific salmon, something that have been connected with El Nino quite a bit. And in part, it's because those climate effects that are teleconnected to ENSO in the tropics affect salmon everywhere they go, in their watersheds, in their estuaries, and in the ocean. And it really depends on where our salmon go. That top right graphic is one that highlights different ocean habitat use and sort of migration routes for different West Coast salmon stocks. So you see that California salmon tend to stay off the California coast, and you go north, those stocks tend to go higher latitudes into the Gulf of Alaska. And what we saw in much of the 20th century is that during the warmer El Nino years, that the northern stocks tended to do better during the warm years, and the southern stocks did worse. And for California, it was sort of a mixed bag, actually. California didn't always follow what happened in the Pacific Northwest, that they really followed the rain. And as Michelle and Nick noted, rainfall in California doesn't always follow ENSO very well. And it's really the rainfall that has driven abundance changes from year to year. And you typically see that a few years after the winter in question, it shows up in adult abundances. Pacific Northwest gets hit with both this unproductive ocean and warmer, drier winters in their watershed. So that tends to be consistently poor. And then in the 21st century, some of these relationships haven't held up. I saw Mike Litzau's name in the attendees list, and he's got a series of publications looking at some of these breakdowns in climate and salmon that are really interesting. So next slide, please. And another thing that's really interesting about this diversity of ENSO impacts in higher latitudes is that you could see it in the coastal ocean as well. And in the California current system, there's a little gray box in that inset, the lower right, that just shows an averaging area for a temperature index that is the solid black curve in this graphic. And then the Niño 3-4 is the dash curve. And I've highlighted some of the big events: 40-41, 57-58, 72-3, 82-3, 97-98, 2014-16. And what you see here is that sometimes these two time series are in lockstep, and sometimes they really don't follow each other. Look at 72-73, big event in the tropics. It was cold on the West Coast. 82-83, the tropical event led the Northeast Pacific by a few months, and that sort of lingered after the El Nino ended. 97-98, more in lockstep. And then 2014 to 2016, look at this one where the Northeast Pacific warmed almost a whole year before the major warming along the equator. So sometimes the tropics leads, sometimes it lags. To get warm water off the West Coast, you need to have that atmospheric teleconnection at work, or at least regionally, we need to have that counterclockwise south winds along the coast. Next slide, please. And then this most recent 3-year La Nina that just ended, I think that's another interesting case. If we take a look at sort of the typical sea surface temperature anomaly pattern with La Nina, and here I've split the year January to June in the left and July to December in the right, and just the 10 strong events from the 20th century into the 21st century, you see that, yeah, we typically have what looks kind of like that big horseshoe pattern of cooling that persists even after the tropical El Nino goes away or La Nina ends. And look at what happened in 2022. In the first half of the year, it at least had that PDO-like arc pattern of cooling, but it was pretty muted. The offshore warm patch was big compared to the composite. And then in the fall, or the late summer through the end of fall 2022, the whole North Pacific was warm. And there was some contrast there, but it certainly wasn't cold. It wasn't anything like the composite. So again, really different event. Next slide. And, you know, looking forward for this year, I'm looking at this map. It's the latest National Multi-Model Ensemble sea surface temperature forecast for August, September, October averages. You know, later this year, the North Pacific is basically surface temperatures are record warm. There's a lot of warm water down to depths of even 200 to 300 meters in much of the central and western North Pacific. And the forecast models are really trending towards development of an El Nino later this year. And I think, wow, if this comes true, there will be some substantial impacts to marine life and fisheries along the Pacific coast, from Alaska all the way down to Mexico. It's going to be another pretty exciting year. That's my last slide.
Well, thanks to all the presenters for.
And I guess it means job security for you. Oh, sorry, Joe, go ahead.
No, go ahead. I think we just ran at a time mostly. I do want to actually field that one question that came in earlier. I've been intrigued by the differences in the tide gauge records between the 82, 83, 97, 98 events compared to 2015, 2016. And Nate, I was wondering if you had any comment on that. I think it's kind of similar to your temperature time series that you showed, but just focusing more on the coastal water level.
Say that again, Joe. I was actually reading the question when you were talking.
Yeah, that's okay. Yeah, it's just the second half of Ian's question. I've been intrigued by the differences in the tide gauge records between the 82, 83, 97, 98 events compared to the 2015, 2016 events.
Yeah, so people have looked in part at what that tropical origin coastally trapped Kelvin wave was like in 2015-16, and I recall it just wasn't as strong as what we had in 97, 98, 82, 83. And then the atmospheric forcing in 2015-16, it wasn't as intense in the Northeast Pacific either, in terms of being right along the coast for the really strong imprint on coastal sea levels and reinforcing that tropical origin coastally trapped Kelvin wave. There was a big persistent area of low pressure that winter, but it was kind of over the Aleutians. It was not shifted towards the West Coast nearly as much as what had been seen in 82, 83 or 97, 98. So it just wasn't in the right place.
Great, thank you. So there were a couple more questions that came in, and we can share those with the speakers, and perhaps we can get some follow-up if they are kind of up their alley. Thanks everybody for your attention. We're going to post this recording. I'll also throw up these slides that talk a little bit about the impact of climate change on El Nino, but most of them are actually a regurgitation of what's on the ENSO blog, so I'll point you to those spots. But thanks again to Michelle, Nick, and Nate for doing a great set of presentations and hopefully raising our enlightenment level for El Nino and North Pacific climate variability. Everyone take care, and hopefully we'll catch you at the April edition of West Watch.
Good one.